Recording has started.
Okay, you may not be totally done yet. Well, let's go ahead and take a look at these problems, see how you've done so far. So number one, this is a half circle, and I'm asking you just find the distance around or the perimeter around this. To do that, we need to find the circumference of a full circle. Now, we could multiply 4 foot 8 inches times pi as it is if we wanted to, because pi technically is not a measurement. It's what we would call a scalar number. It's a non-measured number. But that gets to be pretty complicated to do that. So what I'm going to do in order to multiply this is I'm going to convert the 4 foot 8 into all inches. We can think of this similar to our mixed numbers with fractions, converting from mixed numbers to improper fractions. If you think of that 8 inches as being 8/12 of a foot, it would be 4 times 12 is 48, plus 8 is 56 inches. So we can do 56 inches times pi, or 3.14, giving us 175.84 inches. Well, let's look at what that really gave us. This was the diameter of a circle. And when we multiply the diameter times pi, we get the circumference of a circle. But we get the circumference of a full circle. What we have here is only half a circle. So we have to divide that by 2 to give us 87.92 inches for half a circle. Well, what we got there is the distance around this piece right here. That's the 87.92. We do still have to add this 56 inches back onto it. So we add 56 inches, we now have 133.92 inches. So that's the distance around this. But since the measurements were given in feet and inches, it's proper to give your answer in feet and inches, rounded to whatever units. So I'm going to take my 140, and actually I'm going to show you how to do this in the calculator. So in the calculator, this is in inches. So I'm going to start out by dividing by 12 to make it feet. So I get 11.9933333 feet. That's 11 feet. So I just took out my 11 feet, so I'm going to subtract the 11 off of the calculator, and I'm left with the 0.993333333. I'm going to multiply by 12 again to turn that back into inches. Notice I divided by 12 to turn my inches to feet. I took the decimal part that's left over. I'm going to multiply by 12 to turn that leftover pieces into inches again. That's 11.92. Well, that's 11 inches. And let's say I ask for this to the nearest eighth of an inch. I'm going to subtract off the 11 whole inches. And remember, we talked about taking that 0.92 over 1 to get it to the nearest eighth. You multiply by 8 over 8. So 1 times 8 is 8. 0.92 times 8 is 7.36. Well, that's between 7 and 8 eighths, closer to the 7 eighths. So the distance around that half circle was 11 feet, 11 and 7/8 inches. A lot of steps there, but nothing really terribly complicated. You just have to be able to piece a few different concepts together for that. Number 2 here, we can approach this in a couple of different ways. The perimeter is going to be width plus length plus width plus length. But rather than adding them all separately, what I'm going to do is just going to add the 2 of them. Oops, did somebody have a question? I'm going to add the 2 of them, my 9 foot 10 inches. And I know we're used to seeing them with the feet and inches written out, but it doesn't matter. We can use the abbreviations. 10 plus 7 is 17 inches, which is 1 foot with 5 inches left over. So we'll keep the 5 inches, carry the 1 foot. 1 and 9 is 10, plus 6 is 16 feet. Well, that is this dimension. Get back here. That's this dimension and this dimension added together. We got to double that. So we're going to go times 2. So 2 times 5 inches is 10 inches. That's smaller than a foot, so I don't need to carry anything. And 2 times 16 feet is 32 feet. So it's 32 feet, 10 inches. So I'm going to have you guys try another one just to see how you're doing with these. Oh, let's go 28 feet, 8 inches. 15 feet, 8 inches. I'm going to ask you to find that dimension. Go 16 feet, 1 inch. 12 feet, 6 inches. 10 feet, 7 inches. We'll put this bottom piece at 34 feet, 4 inches. I'll call that dimension A. So I want you to find dimensions A and B for me. I'll give you another minute, and then we'll go over those. Okay, let's take a look at how we find dimension A here. A is a vertical dimension going up and down, which means to find it, we can only use other vertical dimensions. So we have the 15 foot 8, the 16 foot 1, and the 10 foot 7. Well, A is just those 3 dimensions added together. So let's do that. 10 foot 7, 16 foot 1, and 15 foot 8. And we can add them all at once. So 7 plus 1 is 8, plus 8 is 16 inches, which is 1 foot and 4 inches. So I'll keep the 4 inches and carry the 1 foot. 1 and 0 is 1, plus 6 is 7, plus 5 is 12. Well, here we have to carry, just like we do with whole numbers, that's a 2, carry the 1. 1 and 1 is 2, plus 1 is 3, plus 1 is 4. That's 42 feet, 4 inches for dimension A. Dimension B is a little bit trickier. Dimension B is horizontal, so I can only use my other horizontal dimensions to find it. What I see is, what I have to do though, since they're not adding up, some add, some go back, some subtract. And what I need to do is I need to break this into pieces. if I knew this length here in red, I know that would add to the B to make 28/8. Well, that dimension in red is the same as this dimension in red here. I know this dimension and the 12'6" add to make 34/4. So I can subtract to find my red dimension. So 34 feet, I'm going to give myself a little more room there. 34 feet, 4 inches minus 12 foot 6 inches. Of course, 4 minus 6 can't be done, so I'm going to borrow from the 4. That'll be 3. This is going to be, of course, plus 12 inches is 16 inches. 16 minus 6 is 10 inches. 3 minus 2 is 1, and 3 minus 1 is 2. So that's 21 feet, 10 inches across there. So of course, this is 21 feet, 10 inches. So that dimension added with B has to give us the 28/8. So we do the 28 foot 8 inches minus 21 foot 10 inches. 8 minus 10 can't be done, so we're going to borrow from this 8. That's a 7. We add 12 inches here to get 20 inches. 20 minus 10 is 10 inches. 7 minus 1 is 6, and the 2's cancel out, so it's 6 feet 10 inches. Any questions? Okay, well, there is a quiz out there for today. It's quiz 6, also labeled 9-28. That is due by noon tomorrow, so it'll be September 22nd. Now, because this is on the computer screen, there are 2 items on the quiz that you're asked to measure. One is measuring just the length of a line, and the other is measuring the diameter of a circle. Now, I'm trusting that you guys know how to measure the length of the line. The diameter of a circle, you kind of hold the ruler at one side and move it up and down until you get the largest dimension on the ruler, and that's your diameter of the circle. But note what it's asking you to measure to, whether it's asking you to measure to the nearest 1/8 of an inch, 1/16 of an inch, 32nd of an inch, round it to the appropriate unit. Although, remember, 4/16 is still a 1/4 inch. You can still reduce them. Just don't, if it asks it to the nearest 16th, don't give me 5/32 or something like that. Also, if you're not printing these, if you're doing them on the computer screen, make a note of that for me when you submit your answers. Just write next to it or type next to it, I'm done on computer screen. That way I know that your scale may have been off. If you print these, they do print to an exact dimension that I have down. But if you're doing it on the computer screen, the scale can be different. So if you're doing them on the computer screen, let me know so that I can adjust when I grade for that. Okay, well today we finished up talking about units of length. We talked about those units. Here, give me just a second. It's getting a little warm in here. Hopefully my neighbor's done with the chainsaw, so it won't make as much noise. Okay, we talked about all those units of length. The next application, the next step, is to apply those units to units of area. And I want to take a look at the difference between them. Units of length is just a distance between points. So if I give you a unit of 1 inch, that just means a distance from one point to the next. We've moved 1 inch. Units of area, of course, the related unit would be 1 inch squared, or 1 square inch. That's actually a square that's 1 inch by 1 inch that covers a surface that we call 1 square inch. Now with inches, from one to the next, there's really not a whole lot to convert. But if we go up to the next unit of length, 1 foot. Now I'm not going to draw these to scale, but 1 foot just means from where we start to where we stop at the other end of that line is 1 foot long. A unit of area, however, for 1 square foot, of course, is 1 foot by 1 foot. Now 1 foot, however, is 12 inches. So a square foot is 12 inches by 12 inches. Area is length times width. Since this is a square, they're both the same. The area of this is 12 inches times 12 inches, or 144 inches squared, or square inches. 1 square foot equals 144 square inches. Notice it is not the same as the linear conversion. The linear conversion, 1 linear foot, of course, equals 12 linear inches. There's a relationship, however. If I take that relationship of 1 foot equals 12 inches, remember we talked about our rules of equations or equality a little bit, and we'll go over it way more in the next unit. But if I have two things that are equal, if I square one of them, I have to square the other. So to make 1 foot into a square foot, it's 1 squared is 1, feet squared or square feet. For the inches, 12 squared is 144, inches squared is inches squared. That's another way of remembering that conversion, is it's just the linear conversion, 12 inches in a foot, squared to be 144 square inches in a square foot. So if we are trying to convert four square feet into square inches, this is not 48 square inches, which is the most common answer I will get for somebody doing that problem incorrectly. We'll set it up with our conversion factor. That's 4 square feet. We'll put it over 1. Get rid of square feet. We're going to put them on bottom so they cancel out. Go into square inches. Square foot's the bigger unit, so I put the 1 with the larger unit. And we said there's 144 square inches in 1 square foot. So the square feet cross cancel out in our fraction multiplication. We have 4 times 144 is 576 square inches. 1 times 1 is 1, so that's just 576 square inches. So only 4 square feet, and it's already 576 square inches. If I take 3,456 square inches and I want to convert it back into square feet, 3,456 square inches sounds like a lot of surface, because we're more used to seeing things in square feet in the construction fields. That number just sounds huge to us. Well, let's do that conversion. 3,456. We're going to put square inches on bottom here, so square feet will go on top. The square inches went on bottom, so they'll cross cancel. 1 square foot is 144 square inches. Square inches cross cancel. We got 3,456 times 1 square foot is 3,456 square feet over 1 times 144 is 144. We divide. 3,456 divided by 144 is 24. So 3,456 square inches is only 24 square feet. Think of that. That's a rectangle. It's only 4 feet by 6 feet. Not that large. Standard size, nice size room rug is almost 3,500 square inches. In the construction field, calculation that gets made a lot deals with our yards. So a yard of length, of course, is just a distance where from one end point to the other, it's 1 yard of distance. A square yard of course is 1 yard by 1 yard. And a yard is 3 feet. So that's 3 feet by 3 feet. Well, the area of that, 3 feet times 3 feet, well, 3 times 3 is 9, and feet times feet is square feet. 1 square yard is equivalent to 9 square feet. Again, there's 3 feet in a yard. 3 squared, or 3 times 3 is 9. So let's say you have a room in a house that you have measured out, and you have calculated that that room is 279 square feet. Rather large room, by the way. We want to know how many square yards that's going to be for flooring. You see carpet and stuff is sold by the yard. That's technically a square yard. So to convert that to square yards, we're going to do the 279 feet squared, put it over 1 to make it a fraction. Square feet will go on bottom, so they'll cancel out. So square yards on top. 1 yard equals 9 square feet. So the square feet cancel out. 279 times 1 yard, or 1 yard squared is 279 square yards. 1 times 9 is 9. And now we divide it out. 279 square yards divided by 9 is 31 square yards. That's a lot of space, by the way. 25 square yards is a huge room. That's, well, not huge, but it's 15 by 15 feet. That's a pretty large size room for most houses. We might talk about a square rod. Remember, a rod is either 5.5 yards or 16.5 feet. So if I have a square rod, of course that's 1 rod by 1 rod, that's either 5.5 yards by 5.5 yards, which would give us an area 5.5 yards by 5.5 yards of 30.25 square yards, or 16.5 feet by 16.5 feet, giving us an area of 16.5 feet times 16.5 feet, which is 272.25 square feet, I believe. Let me double check that. Yeah, it is 272.25. So if I have land that measures, well, let's just do 100 by 100. So 10,000 square feet. And I want to convert that into square yards. Or square rods, I should say. Remember, rods, the only place rods really get used is in measuring out land and lots. I mean, it's the reason why lots are 99 feet instead of 100 feet by 100 feet, by the way. So anyway, take my 10,000 feet squared, put it over 1. Square feet will go on bottom, square rods on top. 1 square rod is 272.25 square feet. So my square feet cancel out. I have 10,000 rods on top, square rods. 10,000 times 1 square rod is 10,000 square rods. Over on bottom, 1 times 272.25 is just 272.25. Divide that out. I get 36.73 square rods. So 100 by 100 actually is a little bit larger than a normal sized city lot. So a city lot is about 36 square rods in size normally. Well, there was a unit. I'm never going to test you on this unit, but I want to show you this unit just because it explains where some of our other numbers come from. 1 chain is defined to be 4 rods, which comes up to be 66 feet. You're going to see why that's an important thing in just a minute. In land surveying, rods are used to describe lengths from one place to another. But the area of something is often described as a square chain. So a square chain, of course, is 1 chain by 1 chain. Well, that would be 66 feet by 66 feet, giving us an area of 66 feet times 66 feet, or 4,356 square feet. Double checking myself. Yes, 4,356. Why is that important? Well, because there's a unit out there that all of us are familiar with or have heard of at least, and we're all going to see several times in the construction field, and that is an acre. 1 acre, the most common definition you'll see of an acre is 43,560 square feet. And I get asked all the time, where does that number come from? Why in the heck is it 43,560? Well, the reason it's kind of a mystery to most people is they've never seen the unit, the chain. When we see that, we can tell that 1 acre is nothing more than 10 square chains. And that's actually what it was defined as. That's where it came from, is 10 square chains. So an acre was generally a strip of land that was 1 chain by 10 chains. But we've, in our modern society, when we've gone larger units, there was very few things that were 1 acre or smaller. Almost everything was at least 40 acres. So we pretty much a 40 is 20 chains by 20 chains. Let's talk a little bit more about those acres. We are used to a section in most of our surveying being 1 square mile. And I mentioned the term 40. Land is traditionally divided into 40s. What a 40 is 40 acres. A section or a square mile is divided up into 16 40s. One 40-acre piece. All right, that'll look clearer. One 40-acre parcel is 1/4 of a mile by 1/4 of a mile. So it takes the borders of 4 40s add up to make 1 mile long. So a mile, 1 square mile is 16 40s. Or for 16 times 40 would be 640 acres in a square mile. Now, traditionally, roads ran about every mile. So there would be a road on each of those purple lines around here. Actually, many of them in some of the older places, they had small roads that went in from two sides like that to access these inner 40s. Other places, rather than doing 40s, the two inner pieces, actually, that the two of the side pieces were combined with inner pieces on opposite sides like this. So they had 4 40s along one edge, 4 40s along the opposite edge. And then in the middle, these were 80s. It was 2 40s combined, so they didn't have to worry about that access to them. So depending on how that section was blocked off, if they used the 80s, they didn't need these little access roads. If not, they had to have those access roads put in. So this is a little bit of background as to why land is broken up the way it is and where that acre came from. Let's talk a bit about areas now that we have the units. Talking about area, we want to start out with some basic geometry. And in geometry, the most basic shape we can use is this thing right here. It's just a location. It's called a point. Everything in geometry is created from that point. Just like we talked about the number and the count and the name as the two parts of the number being the basis of everything in arithmetic, the point is the basis of everything in geometry. I take that point and I move it in a single direction. I have created a line. Technically, it's a line segment. In practice, we often refer to that as a line, but mathematically speaking, technically a line goes on forever in both directions. So mathematically, that's technically a line segment. It's a piece of a line. But in practice, if we say a line, typically what we are referring to is a line segment. Things that go on forever aren't really useful in construction. The length of that line is equal to the distance that the point moved. So here to here, whatever that distance was, ends up being the length of that line segment. Now this point had 0 dimensions. There's a couple ways of thinking about it. If you're on the point, there's 0 directions that you can move without leaving the point. A line segment has 1 dimension. If you're on that line segment, there's 1 direction you can move without leaving the segment. Well, some might say, well, I can move that way or I can move the other way. That's still just 1 direction. It's just the positive and negative of a single direction. Or the other way you can think of it is that line segment is created by moving in 1 direction or 1 dimension to create that line segment. The dimension itself means it can be measured in 1 direction. Now we can take that line segment and we can move it again in a second direction. Now, the second direction has to be something they call perpendicular. That means it's at a right angle to that original direction. And if you think of this as like a stick being dragged across the sand, it leaves a trace, it leaves its footprint behind as you drag it, it creates a rectangle. And a rectangle is the simplest figure that we have that can actually cover up a surface. In other words, an area. The size of that area depends on the length of the original segment, and once again, the distance moved. This time, the distance moved is often referred to as a width for that rectangle. So area is defined to be length times width, or a length times a distance moved. So let's say that this is 6 inches by 15 inches. The area of that will be the length of 15 inches times the width of 6 inches, or 90 square inches. Of course, I really should indicate square corners and the corners of the rectangle to show that there's right angles, but we're going to assume that if they look like a square corner, if I don't say otherwise, they are a square corner. So I said area could be length times width, but I also said area could be a length times a distance, the distance moved. The reason I say that is technically we do not have to move that original line segment perpendicular. Let's go back to that original 15-inch line segment here. And I'm going to move it once again, but this time, rather than going perpendicular like this, I'm going to move it at an angle. But notice it's staying parallel to its original orientation. I'm just sliding it at an angle, but keeping it lined up parallel. Now, if I think of dragging that stick across the sand, what it traces out in the sand looks like that. Well, as long as the distance from where it started to where it ended, that is the distance moved. Distance is always measured in perpendiculars. As long as that is 6 inches, the area hasn't changed. You can think of it this way. If I cut this into really thin rectangles, if I cut them thin enough, they fit nice and neatly inside this little shape here. This shape's called a parallelogram, by the way. Well, if I push on this to straighten them up, all I'm going to get is this rectangle up here that is 15 inches long and 6 inches high. I've just taken all those little rectangles and split them off to the side a little bit. So that area is still 15 inches by 6 inches, or 90 square inches. Note, however, it is very important that 6 inches goes here from one side to the other. It is not, and I stress not, this length here. This length here is going to be more than 6 inches. But notice that dimension is not at a right angle with that original length. The distance moved has to be perpendicular to that original length of that segment. When we do areas, we have to use two dimensions that are perpendicular with each other. But so since we can turn that parallelogram into a rectangle, we can use that rectangle formula to find its area. Well, in fact, it doesn't even really have to be a straight move like we did there. If I take that 15 inches again, that 15 segment, and I move it, as long as I keep it parallel, I can move it back and forth as I slide. See if I can, something relatively close. And as long as that distance from where I started to where I ended is still 6 inches, the area is still 15 inches by 6 inches, or 90 square inches. So we're coming to the end of our first hour here. I'm going to give you a few minutes to get started on homework. This is out of the big book. Page 296, exercise 8-5, 7 through 29, the odd. And also page 296, exercise 8-6, 7 through 13, the odd. So I'll give you the remainder of this time here to start working on that. We are going to resume lecture at 1:30. So if you need to take a break or whatever during that time, please feel free to go do that as well.
Supposed to be for our table and construction and cabinet making. We all bottom for the whole table. So we thought breakfast food. You want one, you can have one.
Thank you.
Just happy I got that joint done.
Yeah.
Yeah. Which shouldn't be too hard because it should just be the same length as the one I just did. I'm just making a giant hole instead of like trying to like make it fit. I don't know. There's a lot more room for like this thing. The one that I did today, it was like 10 inches long. And I knew I needed to have that 8. So I put it at 8.5 and then cut it. So that way, if I did mess something up, I still have like half to work with. But I didn't mess up, so it's great.
It was like perfect.
Yeah.
I kept pushing it in and out. So lucky.
I still need to take more off though. Because I kept half on there, that's why it's so big.
Yeah.
I still don't understand how we're supposed to do the lines over our computer.
I don't know. I think I may print it out, measure it, and then just put the measurement. Say that I printed it out, but I didn't. Or I'll say that.
Or is there a way where we can just print that page of the test?
Yeah, if we we download it as whatever, take a file and print it,
I don't have a printer on my equipment.
and print a copy for you.
What do you have a printer? Awesome.
The school had a loan, or not a loan, but a on my tongue.
I know the school has computers that are double printers.
Yeah, but they had like a program or a grant. That's what it was. It was a COVID grant. Applying for it, there's a chance to pay for a computer. Or
I'm
whatever.
sure that was probably just for Wisconsin. I'm from Minnesota, so I probably don't have.
It was through this, so you might have been able.
I watch my truck.
Yeah, 10 minutes.
What?
Yeah, 10 minutes.
Oh man, I'm not gonna make it. Sorry, my truck's right outside that door. I can't believe it's already birthday being 4 days.
4 days already?
Yeah. No, it's 5 days would be the 20, the 21st days.
I had to put up gutters on my mom's house.
Very kind, sir. On Sunday, I went to church to go to. So, that's 4 minutes away from. I like watch the church service online. Working, watching. Like when I go back, if I do that though, that room's not there, so I have to. Oh yeah, definitely. Because there's supposed to be, it's a 4-bedroom apartment, but we only have 2. It's just me and my roommate. My roommate hasn't done it. But we each have 2 bedrooms right now. He has one that he uses just for our memory, and then his own bedroom. I have my normal bedroom, and then there's the first bedroom that is unused right now. I want to put the air hockey table in there, and maybe a table or something, and make it like a game room of some sort. I'm also kind of thinking about maybe putting the TV or having that be where we like, because those doors are really like big, so it's a lot nicer to watch movies and stuff and not be. I'll figure something out. I have to move all the furniture in that room though, but it should be. I'm thinking is I might prop the bed stand and everything like up on its side and then lean it against the closet or the little like closet type thing with the shelf. And then I would just move the other stuff into like the other side, the other corner. I have a plan. I just have to figure out how to do it.
Yeah.
Watch not set to go correct.
No. Now it should be close.
How was it?
And I don't know, honestly.
First, which area? How do you spell it? I think I was on watching the math video on Thursday night.
Yeah. This weekend, I've got to catch up on like 20 plus math lessons.
Part of me is I'm just kind of thinking that I should just not do like any of the assignments that aren't gonna hurt my grades. So I would do like the main assignment, but would be the picture frame and just not do the drill bit or results. Because honestly, if I keep focusing on all of that, I'm never gonna get out of it. It's a tricky situation. I want to get grade in that class, but at the same time, if I can just get a grade in that class, I don't know. But part of my plan is to do everything everyone else is doing as far as like where everyone else is. So I'd start with the cutting board and the box or whatever. And then on Thursdays, after like class, I would stay after and then work on stuff that I haven't done. Something quiet thing.
Yeah, sorry.
Just tired. I don't know. I'm always talkative. It doesn't matter. Written 300 points of production and casting just for the work. Which is nice. Long as you get fixed, guaranteed.
I think I'm off by 10 points so far.
Oh. I haven't gotten any of them yet, but there's been a few things that I missed. Pretty good. Well, like our last assignment, it said to like say different frames, drill bits, and tools that you use. The drill bits or whatever, but you like still gave. I don't know.
Fill out that little area with it. I don't think it's like an essay or anything.
No, I don't know.
Just wants us to put something in there at least to show that we were paying attention.
I think that's the whole point of the workbook. Be paying attention. Which is why I always do the workbook with the textbook.
Yeah.
Because before, when I first started, he assigned us like, I don't know, like 30 pages. So I just thought, okay, I'll just read it, it'll be quick and whatnot. And like, I read it, but I didn't understand it. I just read it because I didn't.
Okay, so it's that time again. Actually, I'm a couple minutes late here. Sorry about that. Let's go ahead and get started again. So we're talking about these areas. And of course, the area of a rectangle, where we have a 15-inch by 6-inch. I'm going to stick with that size. That area was length times width. 15 inches times 6 inches give us 90 square inches. course, that big formula, area is length times width. And we looked at the parallelograms and those other odd shapes. As long as the distance from one, what we call the base, to another was that same distance, it was the same area. This is called a base, because that's the line that this shape is based off of. Of course, this is also the base because it starts here and ends there. It's the same base. Well, not all of our shapes can be cut up into those little rectangles, like we said, and pushed around to make other shapes. Some of them are totally different from the rectangle, or at least appear to be at first sight. We might have a shape like this. If this is 15 inches by 6 inches, and we know there's a right corner in there, a right angle, this is what's called a right triangle. We assess the area of that right triangle based on something called a related rectangle. So the related rectangle is a rectangle that would contain this triangle. It would look like that. Well, that rectangle is this one. It's 6 by 15. And we see that that triangle is exactly half of that rectangle. The area of the rectangle will be 15 inches by 6 inches. We divide that by 2 or multiply it by 1/2 to get 45 square inches of area for that triangle. So the right triangle, this is the length of the rectangle. We often refer to that as a base. And then this is the width of the rectangle over here. We often refer to that as a height. The area of a triangle is, sometimes this is 1/2 base times height, or base times height over 2. Either way. I actually prefer the base times height over 2 because that's the way I generally calculate it. It takes fewer calculator strokes that way. Well, this was a right triangle, but it doesn't have to be a right triangle. We just have to be able to turn it into that related rectangle. So let's say this is still 15 inches, but this is not a right triangle. Well, the related rectangle, based off of that 15-inch dimension, would look something like this. There's that related rectangle. What we need to know about that related rectangle is this width here. Well, that width is going to be the way we'd find that dimension from the triangle is we go to the corner, the vertex that is not part of the 15-inch piece, and we measure the distance from that back to the 15-inch piece. Now remember, distance is always measured at a perpendicular. This is often called an altitude, or sometimes just the height of the triangle. If that is still 6 inches, the area of this triangle is still 15 inches times 6 inches divided by 2, or 45 inches squared. Well, you might ask, well, it's not so obvious that that black triangle is half of that rectangle. Well, if I cut it into 2 pieces here, it's pretty obvious that this triangle is half of that portion of the rectangle. And over here, this triangle is half of that portion of the rectangle. Where it's a little less obvious is if we have a triangle looks something like this, where this is still 15 inches across here. But now the related rectangle for this is not really obvious here. Because if I draw in this rectangle, that triangle is not half that rectangle, it's less than half of it. The related rectangle for this actually ends up being this. Now you might say, well, that brown, that tan rectangle, if you want to, it's not obvious that that triangle is half of that tan rectangle. But what we can do is this. I'm going to draw a big green rectangle like this. and then a smaller blue one. That tan rectangle is equal to the green rectangle, the area of the green rectangle minus the area of the blue. Well, the same is true for the triangles then. This big triangle here is half of the green rectangle, and this little triangle here that's missing is half of the blue rectangle. So half of the green minus half of the blue equals half of the tan. So that tan rectangle is still the related rectangle, even though it's a little bit harder to see. And if you didn't catch my explanation, that's okay. You don't need to understand it. What you need to understand is we still need this height of that related rectangle. That height is measured still from that opposite vertex away from the side that we know. The 15-inch side has these two corners touching it. We want the other one that doesn't touch it. And the distance to that 15-inch side. However, the distance is always measured perpendicular. And there's no way from that point to that side inside the triangle that's perpendicular. But outside the triangle, if we extend that 15-inch base out, that height or altitude comes down to it like that. If that is still 6 inches, the area of this triangle is still 15 inches times 6 inches divided by 2. 45 square inches. Of course, I've been drawing all these triangles with a base on bottom. Isn't necessarily true that the base is going to be on bottom. Any side of this triangle at this point could be its base. I haven't written in any dimensions. The base of a triangle is any side that we know the length of. So if I tell you that I know the length of this is 24 feet, that becomes the base of that triangle, if that's the only side. If I know multiple sides, I can pick which one I want to use if I have the other information. Of course, now then, the altitude or the height has to come from the opposite corner. That's this corner over here. And to measure that back, it's going to measure something like this. To extend this out, and let's say that is 32 feet. Now the area of this triangle is going to be found by doing that base of 24 feet times that altitude or height of 32 feet divided by 2, which is 384 square feet. Just going to double check that because it's been one of those mornings, one of those days. It is 384 square feet. So all of our shapes, the areas of all of our shapes come from related rectangles. Let's look at some other shapes and see how they come from. Well, we have a shape called a trapezoid. A trapezoid is defined to be a four-sided shape with one pair of parallel sides. What does that mean? One pair of parallel sides. Well, typically we see a trapezoid drawn something like this. So this is what's called a base, and this is also a base. Those are the two sides that are parallel. Those are the bases of the trapezoid. Note that I wrote one of them with a small b and the other one with a large B because they're not the same length in a trapezoid. So I need to be able to distinguish between them using a capital B and a small b. So let's say that this base up here is 18 inches long. This one down here is 32 inches. And the distance between bases, because that's what we used in our rectangles and parallelograms and stuff, let's say that's 20 inches in between. How can I turn this thing into a rectangle? Well, I can go halfway down this sloped surface here, right about there is halfway down, and cut that off square. Well, this piece that I cut off here should flip up and fill in here just perfectly. I just squared off one end of that trapezoid. I can do the same on the other end. I go halfway down, I chop this off, flip that piece up, and it fills in the end of the trapezoid. I now have a rectangle. The rectangle here has a width that's just equal to that height of 20 inches. That's just equal to the height of the trapezoid. The length is the trickier part. The length here is longer than the small base, but smaller than the big base. In fact, it's exactly halfway in between. How do we find what's halfway in between? We average the bases together. So the length of our rectangle is the average of the two bases. You add them together and divide by 2. The area for a trapezoid is the average of the bases, the height. So for this trapezoid, it'd be 18 plus 32 divided by 2 times that height of 20. 18 plus 32 is 50. 50 divided by 2 is 25. 25 divided by 20 is 500. Those were in inches, so this is square inches. So that area is 500 square inches for that trapezoid. Well, not all trapezoids sit flat like that. A trapezoid can be any four-sided shape with one set of parallel sides. So this is a trapezoid. Let's say that this up here is 8 inches. Let's make this here 15 inches. And this piece down here, we're going to make 24 inches. Of course, we do have to tell you that 15 inches is perpendicular to the bases, because that's to be a height or distance between, it has to be perpendicular on both ends. So the area, the bases are the 8 and the 24. 8 plus 24 over 2. We average those. Then we multiply by that height of 15. 8 plus 24 is 32. 32 over 2 is 16. 16 times 15 is 240. Those were in inches, so this is square inches. So a trapezoid comes from a rectangle as well. Well, the next one I want to talk about is circle. Well, you might be thinking, well, there's no way a circle comes from a rectangle. But it does. Some things to review. Of course, this is the diameter of a circle. From the center out is a radius. The diameter of a circle, which I'm just going to abbreviate D, is equal to 2 times the radius. The circumference distance around the circle. The circumference is equal to the diameter times pi. Or now that we know that diameter is equal to 2 times the radius, it can be 2 times the radius times pi. So what I'm going to do now is I'm going to take this circle that I have. I'm going to cut it in half. This distance from here around to here is half the circumference. Well, if the circumference is 2 times radius times pi, half of that would just divide out the 2. So the distance around this is just radius times pi. Well, I'm going to take that half a circle, I'm going to cut it into really thin slices, really thin pi wedges, just like those little thin rectangles we cut out of our parallelogram. And I'm going to take those little slices and I'm going to fan them out. And I get kind of like a sharp-toothed comb like this. What it ends up looking like. Remember, this is just the radius of the circle. That's this dimension right here. This, if I cut those slices thin enough, is just the radius times pi. Well, I still have another half of that circle. If I take the other half of that circle and I cut it in equally thin slices and fan them out, they should exactly fill in those missing, between the teeth of the original slices I fanned out. I didn't draw them in real well, but you get the point. So if those slices are thin enough, this is now basically just a rectangle. The length of that rectangle is radius times pi. The width is radius. R times pi is radius squared times pi, or the formula that we all know for the area of our circle, pi times radius squared. So even a circle comes from a rectangle. By the way, this strategy that we did here of cutting it into thin pieces, up in the parallelogram we cut it into the thin rectangles. Here we cut it into little thin slices so we could essentially make a rectangle. That's really the theory of calculus. Now, we're not going to do calculus in here, but since we kind of did that example, I wanted to mention that's what calculus is basically a mathematical way of slicing things into small enough slices that you can turn it into a rectangle, turn them into rectangles. Pretend that looks like a circle. We have a radius of 4 inches. If I want to find the area, that's pi times 4 inches squared. 4 squared is 16 times pi is going to be 50.24 square inches. Now, what I did there is I used 3.14 for pi. You get 50.24. 3.14 times 4 squared. You get 50.24. However, most of your calculators have a pi key, and some of you might decide you'd rather use the pi key. That is fine. If you want to use that pi key, there it is. If you're going to do that, though, you're going to get a slightly larger answer. It'd actually be 50.26 when you round it. 50.27 actually here. On a quiz or a test, I just want to assure you that I do the answer key both ways, and I'll accept any answer in between them. So that could be considered 50.27 square inches if you use the pi key. They're equivalent answers, it's just different rounding. So for this circle, we have a diameter of 10 feet. To find its area, it's pi times 5 feet squared. Where'd the 5 feet come from? Oh, 10 was the diameter. We need the radius for the area. So it'll be half that, 5 feet. Again, if I use 3.14, that comes out to 78.5 square feet for that area. Some things that we want to use our areas for. Pressure is defined to be force divided by an area that it's spread out on. In construction, if we have a 6-inch by 6-inch post. Now to make it simple, we're going to assume that it's full 6 inches by 6 inches. We all know that in reality, what they say is a 6 by 6 post is actually 5.5 by 5.5, or sometimes even 5 1/4 by 5 1/4. But we're going to say it's a 6 by 6 inch square post. That has an area 6 inches times 6 inches, or 36 square inches. And let's say it is supporting a weight of 7,200 pounds. That gives us a pressure. 7,200 pounds is our force, divided by 36 square inches. It's 200 pounds per square inch. That sounds like a lot of force. Standard construction lumber has an allowable stress or pressure of 1,250. So 1,150 or 1,250, depending on the application, pounds per square inch. So 200 pounds per square inch sounds like a lot of weight, but that is actually pretty safe on that post. If you ever used a wood splitter or even a loader or whatever, you've seen hydraulic rams.
Yeah, I didn't either. Right, Matt was gonna do his bathroom. I just seen Dave, I'm like.
So let's look at the hydraulic ram here. Hydraulic ram works off of hydraulic pressure. So let's say that we have a pump that is putting out 250 psi, that's pounds per square inch. And this is a 4-inch ram. The area is pi times 2 squared. Where did the 2 come from? Well, again, 4 inches diameter, 2 inch is the radius. That ends up being 12.56 square inches of area. Well, the formula we had was pressure equals force divided by area. But we could rearrange that formula to say that the force equals the pressure times the area. So the amount of force that this ram can push out with is that pressure of 250 pounds per square inch times 12.56 square inches. 250 pounds per square inch is a very, very weak hydraulic pump, by the way. Most of them run well over 400 pounds per square inch. That's still 3,140 pounds of force that can push out with. So a log splitter, you think it doesn't sound like it's a 200 pound or 250 pound on those small hydraulic pumps, the compressors. You don't think that's much force, but that's putting out 3,000 pounds of force on that splitter. Well, the one thing we have not talked about yet is metric units of area. We're not going to talk about metric land area. The unit of metric land area is actually something called an R. An R is 10 square meters by 10 square meters. It hasn't even caught on in European countries where the metric system's been used for almost 30 years now. We're just going to stick with square meters, square centimeters in our standard length units. So if you recall our length units, our major unit of length was the meter. If I wanted to measure something smaller, there's a decimeter, it was a tenth of a meter, centimeter was a hundredth of a meter, millimeter was a thousandth of a meter. Going larger, decameter was 10 meters, hectometer was 100 meters, and kilometer was 1,000 meters. If I had 720 millimeters and I wanted to convert it to meters, from millimeters to meters is 1, 2, 3 spots to the left on the chart, which means I move my decimal point and my number 3 spots to the left. Now there's no decimal point here, so it's at the end of the number, so it goes 1, 2, 3. That's 0.72 meters. If I had 3.8 centimeters, and I want to convert it to millimeters. From centimeters to millimeters is 1 spot to the right on the chart, so my decimal point has to move 1 spot to the right. That's 38 millimeters. The reason we could just move the decimal point is every spot on the chart, when we're talking about length, is either multiplying by 10 or dividing by 10 as we move through it. When you multiply by 10, it moves the decimal point 1 spot to the right. You divide by 10, it moves it 1 spot to the left. So we could just look at the movements on the chart and move our decimal point that number of spots. Well, if we're going to talk about units of area, if this were 720 millimeters squared, going into meters squared, with our standard units, the area units were just the linear conversions squared. 3 feet in a yard, so 3 squared or 9 square feet in a square yard. Same type of thing here. Each of these conversions is multiplying or dividing by 10 for length. For area, they're either multiplying by 10 squared or 100 or dividing by 100, which means every spot on the chart is 2 decimal places. So going from millimeters to meters is still 3 spots to the left on the chart, but since it's meters squared to millimeters squared to meters squared, each spot on the chart is 2 decimal places. So 3 spots on the chart is 6 decimal places. So here's my decimal point. I have to go 1, 2, 3, and then I have to add zeros. Go 4, 5, 6 spots. So 720 millimeters squared is 0.00072 meters squared. .8 centimeters squared to millimeters squared. Well, centimeters to millimeters is still only 1 spot on the chart. But now, since it's centimeters squared to millimeters squared, each spot is 2 decimal places. So 1 spot on the chart is 2 places on my decimal. I have to go 1, 2, I have to add a 0. That's 380 millimeters squared. In your notes, convert for me. 0.091 meters squared into centimeters squared. And .720 square inches into square feet. We'll go over those in just a minute. So from meters squared to centimeters squared. On the chart, from meters to centimeters is 2 spots to the right. Since it's squared, each spot on the chart is 2 decimal places. So my decimal point has to go 4 spots. There are 1, 2, 3, and I have to add a 0 to go 4. 910 square centimeters. For the 720 square inches, I'm going to use the conversion. For standard measurement, I tend to resort to the conversion factors. Square inches to square feet. 1 square foot's 144 square inches. Square inches cancel out. 720 times 1 square foot is 720 square feet. 1 times 144 is 144. We divide 720 square feet divided by 144 is 5 square feet. Any questions there? We'll give you some time to do homework. There's 2 pieces here. The first piece is out of the little book. It is units 21 and 22. Again, it's the odds. Out of the big book, there's a couple pages. Page 320, exercise 9-5, problems 7 through 21, the odds. The reason it's 7 through 21, by the way, is that 1 through 6 are review problems from earlier sections. If you're worried about remembering information we previously learned, doing those 1 through 6 problems is actually a pretty good idea. It's a review of stuff we've already done. And then page 321, exercise 9-7, problems 7 through 12. And don't forget, there's a quiz sitting out there. It's quiz 6, 9-25, I believe. Or is it 9-28?
Yeah, it's 9:28.
Due by noon, September 22nd. Okay, so I'll be on the network here for a while if you want to stick around and work on your homework for a bit.